the 2x2 table. And if we look at our fitted model, here's our fitted model. The estimate for the intercept is minus 0.52. More importantly, the estimate for the coefficient of the Ohana intervention variable is minus 1.01. We've said many times that that's an estimate for the log odds ratio. We're measuring the association between the Ohana intervention variable and our outcome variable, death. And if we turn that into an odds ratio by taking e to that number, we get the same odds ratio, 0.36, the same confidence interval, 0.25 up to 0.518 that we got for the 2x2 table. So this is a crude analysis. This is controlling for nothing. This is looking at the crude relationship between the intervention and the outcome, not adjusting for any potential confounders. And we're concerned that Table 1 suggested that all these potential confounders may well be confounders. They were not balanced in the two groups we compared. So we have a need, I think, in this analysis to control for factors like age and sex and body mass index. So let's do that today. Let me go back to the editor. And first thing to do is, let's suppose we only want to control for body mass index. And we'll do it a couple of different ways. The first thing is I want to fit a model that says your log odds of dying depends on your intervention, Ohana 1 or 0, 1 if you got the intervention, 0 if you didn't, but also depends on your body mass index. In other words, let's assume that your risk changes within each of these communities with body mass index. We expect people with very, very large values for BMI to have higher risks of dying, higher odds of dying, higher log odds of dying than people with lower body mass index. So we're going to fit a model including body mass index as an added covariate. But now we're making an assumption. We're including it as a single term, including it as a continuous term. And what we're assuming is a linear relationship. In terms of those slides we looked at a few minutes ago about blood pressure, we're making that same linear assumption now about body mass index, but we're saying conditioning on the intervention status, meaning looking separately within people who received the intervention, or separately within people who didn't receive the intervention. We're assuming there's a straight line relationship between your body mass index level and your log odds of dying. So let's run this model and see what we get for outputs. So I'm going to highlight that and run it. SAS just gives me that output at the bottom of the output window. What I'll do is I'll go to the results window, click on the various parts of that job I just ran. Let me go to the beginning of this output. So here's the beginning again. Looks the same thing. I got the 172 people who died and the same 500 people who didn't die. But now everything else on this slide, on the bottom of this slide, is changing. Well, not everything, a few things have. It talks about model fit. Let's look at the minus 2 log L. The same number, 764.441, we have for the intercept only. In other words, if you just did a model which assumes everybody has the same risk of dying regardless of their status for the intervention and regardless with respect to body mass index, that model would fit the data with a value of 764.441 for the value of minus 2 log L. But now we're fitting a model with two covariates. Ohana, the intervention variable, and the body mass index variable, and on top of that, we're making assumptions. We're assuming that the relationship that body mass index has to your log odds of disease, conditioning on your intervention status, in other words, separately within each of these two intervention groups, it has a linear relationship. And it says, for that model, the value for the minus 2 log L dropped from 764 down to 712. So notice if I go back to the previous model, the model with just the Ohana variable, went from 764 to 732. Now, in the model with two covariates, it's gone from 764 even lower down to 712. It's dropped 764 minus 712, it's dropped 52 points. And that drop in points, 52, can be used to test the fit of the model with the intercept and the two covariates to the model with the intercept only. And what it does, it looks it up in a chi-squared table with 2 degrees of freedom. The reason there are 2 degrees of freedom is because we're comparing two models, one with only a B0 term, the intercept only, and one with a B0 plus a B1, the coefficient of Ohana, plus a B2, the coefficient of BMI. The intercept plus covariates have used up 2 degrees of freedom by including 2 additional terms in our model, requiring us to now estimate a B1 and a B2. But if we look up the number 52.0974 in a chi-squared table with 2 degrees of freedom, we'll get a very, very small p-value, meaning that this data, with this test statistic, doesn't support the global null hypothesis. So let's make sure we understand what the global null hypothesis means. The global null hypothesis means that all the coefficients of all the risk factors are equal to 0, meaning that as a set, the intervention variable HANA and the body mass index variable, BMI, as a set, don't influence your risk of dying. Both of them have coefficients of 0 if the global null hypothesis is true. And this data tells us the test statistics, 52, with its very, very small p-value, p less than 0.0001, does not support that global null hypothesis, meaning the data suggests that one or both of the covariates do matter. They do change your risk. But the problem is you don't know from this page of the output whether it's the Ohana variable that matters or it's the BMI variable that matters in terms of changing your risk, or if it's both variables that matter. All we know is that as a set, the two of them change your risk. But we really want to know whether it's the Ohana variable that has an independent relationship, whether that dotted line on that causal diagram exists, whether controlling for BMI, the Ohana variable, is related to your risk of dying independently of body mass index. And we're going to be seeing that if we look at the fitted model. But before we do that, let me just point out one other piece of information on this printout that we haven't talked about before. There's this number AIC, or this label AIC, as a criterion for model fitting. AIC, I think I might have mentioned, stands for Akieki's Information Criterion, named after the Japanese statistician Akieki, who developed this information criterion. And notice the value for the AIC for the model with the intercept only is 766.441. It's 2 points higher than the -2 log L value. Notice for the model with the intercept and covariates, the value for the AIC, 718.346, is 6 points higher than the -2 log L. What the AIC is saying is, let's penalize a model fit 2 points for every coefficient it has to estimate, to penalize big fitting models that would be very cumbersome, very inefficient. Because remember, we like to have all things being equal, -2 log L to be close to 0. And it turns out the -2 log L will always get smaller when you build bigger models. A bigger model will always give you a value of -2 log L that's smaller than the value for -2 log L for a previous model that didn't have all those coefficients, as we see here. Notice the -2 log L went from 764 down to 712 when we added more factors. Even if those factors had no real influence on your outcome, even if just by chance they were related to the outcome, you'd still get a drop in the -2 log L. What Akieki says, I'm going to charge you 2 points for every risk factor you put in the model. But even though the -2 log L will get smaller as you add more factors to the model, the AIC statistic will not, unless the drop in the -2 log L is more than 2 points. Because AIC is going to charge you 2 points for every factor you add. So maybe what we should be monitoring also is this -2 log L value and the AIC value for the intercept and covariates when we want to compare different ways of fitting a model. So in a minute, when we look at different ways to control for body mass index, and we're deciding which of these different models that control for body mass index seems to fit our data set better, one option is to go with the model that has the -2 log L that's smallest. But maybe a better option is go to the model which has the AIC that's smaller, and we'll see that in a second. So just keep that in the back of your minds for a second. We'll get back to that in a minute. But let's look at the fitted model. Let's look at the parameter estimates. So I'll click on that. Click again. There we go. Here's our final model. It says your log odds of dying is -2.3.